In this recording, we'll discuss a little bit the math that we are going to be using in this course to describe motion and whatever other topics we are going to cover. Now, we are not going to use trigonometry in this course, meaning the sine and cosine functions and so on. We're not going to use them, of course. That means also we are not going to use more advanced topics like calculus, differential equations, and so on. But we are going to use a little algebra. We are going to have to solve equations with one unknown, or sometimes equations with two unknowns, two equations with two unknowns. We are going to have, so we are going to solve linear equations with one and two unknowns. We will solve as well quadratic equations. Excuse me. Now, I'm aware that some of you are teaching middle grade, and unfortunately, the middle grade curriculum does not ask of the students in physics, in physical science, to use this kind of math in their work. And that's fine, actually, but then students at that level are exposed at least to linear equations. They know also how to calculate slopes. We are going to use slopes as well. Quadratic equations, they do not do them, I believe, but it's still not a big step above what they can do. So that's one of the things we'll be able to do. One of my philosophies is the teacher should become more comfortable of using the math. When they become more comfortable, it makes that would translate in the way they teach and make the students feel more at ease at using those concepts. Now, one thing that we'll be talking about without using trigonometry is what we call vectors. We are going to talk about, because vectors are very important in talking about motion and forces, because it's through vectors that we account for direction as well as the value of the quantity that we are using. Okay, let's go to the next screen here. I'm going to try to run here an application. This is from, actually, I don't have the address written correctly, but it's supposed to be, let's go back to the pen so I can write it. It's supposed to say fet.colorado.edu. And vector addition is actually separate. That's me explaining what the simulation is. Once you go to fet.colorado.edu, you search for it and you find it. One thing nice about the FET simulations is they allow you a download, and actually the version that we are going to run right now, it is on my computer here, downloaded on my computer. So I'm going to click on it. It tells me to worry and stuff like that. I'm not worried. I know what I'm doing. So it's going to come up here. Okay, I'm going to use F11 to block all the menus. Okay, here is our simulation. Now, the nice thing with this simulation, we have a grab box here. We can grab vectors with it. Okay, here's one. Okay, as you notice, vectors are actually arrows. They look like arrows. That's a way we represent them. We represent them by arrows. Now, those arrows have a length and a direction. Look here, when I clicked on it, we see that information. This R here, with an absolute value around it, tells us of the length of that arrow. The length of that arrow, we call it magnitude. And theta here is the direction. But then there is something else. We can find these if we do calculus, if we use trigonometry, but in our case we are not. But this tells us how much of the arrow is parallel to the x-axis and how much of the arrow is parallel to the y-axis. And actually we can show that. This is how much of it is parallel to the x-axis, and this is how much of it is parallel to the y. Now I'm going to change that arrow a little bit so we can see how, as I change it, this is the overall size of the arrow or magnitude of the arrow. This is the angle relative to the x-axis. This is how much of the arrow is along the x and how much of the arrow is along the y. Okay. What I'm going to do, I'm going to add another arrow. Okay, let's do it this way. And then add another arrow. Let's go this way. Okay, this one is 10.6. The angle is minus 48.8 degrees. We have an amount that's equal to 7 along the x, and minus 8, we have the minus to tell us it's pointing down. Okay, now we can see things some different way. How much of it is along the x and along the y, we can represent it this way. Okay. Now, what I'm going to do is tell it to show me the sum of these vectors. Okay, so I click on it, and that's what it showed. Okay, now how do we do the sum? What I'm going to do, I'm going to remove all these other components and come up with one of the arrows, and then at the tip of that arrow I add the other arrow, and then at the tip of the other arrow I place the third arrow. And look here, the sum, you get it by joining the tail of the first arrow to the tip of the last arrow. That's the way we get the sum. Now another way of looking at it is through the x part and the y part for each one of them. Now if we go back, if we focus now, if you look at the x parts, we have 2 towards the right and 1 towards the left. So the sum is going to be towards the right. That's what we see here. And along the vertical, along the y, I have 2 up and 1 down. So the overall is going to be this. Actually, we can even quantify that if we want. Okay, now when we look at this one, so it is it's not showing me actually the values so anymore. So let's remove the sum so we can see. No. Okay, so it's too late. This shows only the sum. Okay, anyway, so when we add up these values, this is going to be a positive value plus a positive value plus a negative value. That will give you what we get here for the sum, and so on. Okay, but the key thing here, I'm going to clear all of these, and I'm going to have a vector along the x, and I'm going to have another vector along the x, but in opposite direction. This one is 14, this one is 11 in size. One is pointing negatively and one is pointing positively. Now, what's the sum of these two vectors? 11 towards the left, 14 towards the right. So it should be this one, which is 3 towards the right. And that's what we see. So when vectors are along the same direction, we just add them up simply algebraically. You take your positive one, and this one your negative one, and you just add them up. I could have done this along the y-axis. It should not be any problem. Now, let's change this. Okay. Now, this one here, the size now is 18.4, but the size along the x is 17. The size along the x for this one is minus 11. 17 minus 11 should give us 6. So if I go here, that's what we get, 6. So whatever is along the x is not affected by what we have along the y. Let's check the y. This one has a y component of 7. A y portion that is 7. This one has 0. So the sum should be 7. And that's what we see, 7. In other words, when we deal with vectors, what vectors allow us to do is to separate whatever is acting along one direction from whatever is acting along the direction perpendicular to it. That's the key point. We don't mix and match. If I have a vector at any random direction like this one, when we are going to deal with it, we are going to have to deal of how much of that vector is along the x, separately from how much of that vector is along the y. And that's applicable to all vectors. One last thing, one last reminder, the length of the arrow tells us how big is that vector, or what we call its magnitude, and then the way it is pointing, the way the arrow is pointing, gives us the direction of that vector. So again, a quick summary, vectors have a direction and a magnitude. The direction is given by the way the arrow is pointing. The magnitude is given by the size of the arrow. When we add vectors along the same direction. We don't add vectors that are along different directions. When vectors are along different directions, we worry about their portions. We worry about how much of a vector is along x and how much is along y.